If you are watching this video for the first time, please do the warm-up before I start talking. Press pause now and do the warm-up. Okay, let's go over this. In Calculus 1, we thought of the area as the sum of rectangles, and each of these rectangles had a really small, incrementally small width, and so when we set up the integral, we added up those rectangles as an infinite sum, and so the area was the infinite sum of rectangles from 0 to 2, and then the height of every rectangle was the function 2x minus the function x squared, and then dx was that width, and then the remaining work is shown here. Should be straightforward. Now, as we get into iterated integrals, or in this case double integrals, instead of thinking of this region as made up by a bunch of rectangles, think of this region as made up by a bunch of little tiny squares where both the width is incrementally small and the height is also incrementally small. Now, I'm going to draw circles, but really what I mean are squares, and each of those squares added up defines that region, which is lightly shaded gray. So now, if we were to infinitely sum those little rectangles, but we were summing them from 0 all the way up to 2, and then summing them from y equals 0 all the way up to y equals 4, if we did that sum, then I would be going from 0 to 2, and then I would be going from 0 to 4 of those little squares, and those little squares can be represented by dy dx. And more to come on this, but if you were to do these what are called rectangular bounds or fixed bounds, you would get this pink shaded rectangle. You would find the area of the pink shaded rectangle, which is not what we want. We only want that gray sliver inside there. So now think of the area. We see these two vertical bars. Think of everything inside those vertical bars, and within those vertical bars we are going to stack up these little squares that start at the bottom curve and go up to the top curve. So if that's the approach that I'm using, then I'm fixing the x's to be between 0 and 2. So we're counting everything between 0 and 2. But then when I'm adding up the squares, again, I don't want that full rectangle. I only want, pick a different color. I only want to start from here and I want to end up here. I want to start from y equals this curve, and I want to keep adding up the squares going up until I reach this curve. So the bounds on that will vary. The lower bound will be the parabola of x squared, and then the upper bound will be the linear equation 2x. And the thing that we are summing up, again, are these little increment squares, which is dy dx. I would like to note here that this outer integral matches up with this outer variable of integration. So notice the dx is written here, so the outer integral bound is x equals 0 to x equals 2, and then the inner dy is matched up with the y bound. And just for some terminology, the fact that the lower bound of y is always x squared and the upper bound of y is always 2x, and that's going to be true throughout the entire region, we call this a type 1 region. So type 1, if you think of it in terms of rectangles, says the top of the rectangle is always the one curve and the bottom of the rectangle is always the same bottom curve. Now we're going to approach the same area, but in a different approach. We're going to say within these horizontal bars, y equals 0 and y equals 4. Within those, we're going to think of adding up a bunch of squares going across. So we're going to fix the y and then vary the x. In that case, we're going to have the integral from 0 to 4. So my outer variable of integration is going to be dy. And then within that, again, I can't say from 0 to 2 here, it gives me the full rectangle. I don't want the full rectangle. I want to go from this curve out to this curve as I sum up those little tiny squares. So I need to obviously solve for x in this case. So this is going to be the linear portion, which is y over 2 is the lower bound of x, and the upper bound of x is going to be the square root of y, and this time it's going to be dx dy. So we have to fix the outer, and then within that fixed, we're going to vary the inner. Now after the warm-up, we have a couple numbered items in the notes packet, and this is number 1. We're going to give some contextual meaning to these double integrals, and here I have f of xy, and f of xy can mean a whole host of things. I'm going to pick a couple of them just to illustrate what the double integral could represent. Suppose that f of xy represented the density of some plate, let's say, this is the density at some point xy, then the double integral would give us one meaning. Suppose that f of xy gave us the height of a mountain, or the altitude, or perhaps the depth of a lake. Well, then the double integral would give us a different meaning. And I'm going to leave this last one blank here intentionally just for a moment. So if f of xy gave us the density, and I'm summing up over the region, let's say I'm summing up over a gray shaded region for all the density points, then what would that give us? Well, hopefully you would see that would give us the mass of that 2D plate, so the gray shaded region like we did in the warm-up. If f of xy was present and represented the density, then this total double integral would give us the mass of that 2D plate with shape r. Now for the second one, if f of xy equals the height of the mountain, and I integrate over that shaded region r, and at each point xy there was a height, then can you imagine what the double integral would represent? And I am hoping that you recognize that to be the volume of some solid, where the base of that solid is the region r. And in the final one, suppose I wanted this double integral to give me the area of shaded region r. Then f of xy must be equal to something in order for that to be true. Can you guess or figure out what f of xy must equal in order for us to have the area of a shaded region? And if you're guessing 1, then you are correct. And in problem 3 of the notes, we will work out the area to find that it also equals 4/3 using these double integral techniques. Now, number 2 in the notes is a repeat. I just want to explain again that R means some region. I like to say shaded region, and the dA, I probably should have mentioned that before. That's saying the incrementally small square, so that could be dx, dy, or it can be dy, dx. And if I leave it dA, I do not have to specify the order. And so what I wanted in this problem is to keep this f of xy generic or general, and do it where we have dy dx, which is what we talked about earlier. So the x is fixed, and so that's going to be simply 0 to 2 like we did in the warm-up, and then the y is going to vary from x squared to 2x. And then that equals the integral, double integral, of f of xy, this time dx dy, meaning fix the y, and the y was fixed to be 0 to 4, and then the x varied from y over 2 to the square root of y. Now in number 3 of the notes, we're going to go back to the area problem, and we're going to solve it to kind of show you the technique of the iterated integral. There are 2 integrals, so we can say double integral. It is iterated because you do an iteration to do the actual integration. Let's look at the first one. You might notice that f of xy here is equal to 1. I just wanted to reiterate that's a coefficient of 1, so this does represent area. Now an option is to write the double integral like this. I don't advise it, but it is an option because it kind of shows you the process at which we do it, or the order in which we do it. I'm going to do inside first. So I'm going to find the integral of 1 with respect to y, And the integral of 1 with respect to y is simply y. And then y is going to go from x squared to 2x, and then we still have out here the trailing dx. So I'm working the inner part first. So now we have the integral from 0 to 2, and just like the fundamental theorem of calculus, I'm going to plug this in first, and that's going to give me 2x minus, then I plug in the bottom bound, fundamental theorem of calculus, x squared, and then I still have the trailing dx. And what's really cool, this is exactly what you set up in the warm-up to find the area. And that, of course, equals ... We already know that it equals 4/3. Let's do the next one. Okay, this time I'm going to leave the outer bound, 0 to 4, the fixed bound. I'm going to work on the inside, and the integral of dx with respect to x is simply x, and that's going to go from y over 2 to the square root of y, and then we have the trailing dy. And using the fundamental theorem of calculus, we have the square root of y minus y over 2 dy, and of course you can do that simple integration as well, and that comes out to be 4/3. It's possible that in the warm-up, when you're asked to find the area, you very well could have thought of the rectangles going this way, in which case you would have got exactly what we just did in the part number 3. And I do want to point out, in case I failed to mention this, this is now called a type 2 region, because everywhere in this region, the top or rightmost point is always one curve, and the left or bottom is always the other curve, and that's consistent throughout the entire region, making this a type 2 region. So this particular region is both a type 1 region, there's the indication of a type 1, and a type 2 region. In number 4 here, we're going to do a little more integration. You will notice that the bounds are the same as the ones we've been working on. The difference is here I'm giving some function f of x, y. So remember, this has a different contextual meaning. If that f of x, y was height, it's the volume, so on and so forth. We are going to work what's inside the blue first, and then the outside integral 0 to 2, and then the dx will go along for the ride. So let's integrate inside this. We need to integrate this expression with respect to y. So now the integral of x cubed with respect to y, we treat x cubed like it's a constant, and so then it's just going to be x cubed y plus, now the integral of 4y with respect to y is going to be 4y squared over 2, and that reduces to 2y squared. And that, of course, is going to go from x squared to 2x, and then this dx is going along for the ride. Fundamental theorem of calculus, I need to plug the 2x in for all of the y's, and that'll give me 2x to the 4th plus 8x squared. And then when I plug the x squared in for the y's, that's going to give me x to the 5th plus 2x to the 4th. All right, let me put my bracket around that, and then it will be with respect to x. And then going forward here, it's exactly like regular integration.
Math is my favorite subject. Why go to school? Take AP calculus with my friends. It makes me feel cool.
And I think it's important that even though you know how to do it, I think it's important that you do the grind in this course. Grind out these integrals to get that final answer. Now we're going to do the integration where we reverse the variables of integration, and I would like you to press pause now and grind this out. And I mean it. To get the full experience, press pause and grind this out.
Math is my favorite subject. Math is so cool. If it wasn't for mathematics, I would be a fool. chain rule.
This next problem is very important. We are finding the double integral, or at least expressing this double integral in two different ways, where R is the region bounded by these three curves. So let's draw these three curves to get a sense of the bounded region. I do wish you were doing this without my assistance, but we'll just do it together. Let me pick some different colors for the different curves. So x equals y cubed. So that's going to come down and do one of these. And then we have the line x plus y equals 2. 1, 2, 1, 2. That's a line. Let's see if I can draw this line. Okay, good enough. And then, of course, y equals 0 is the x-axis. So here we go. So the region R bounded between those three graphs is this gray shaded region here. And so first we're going to find the integral over region R of f of xy, but we'll do it with dy dx. Now analyze this carefully, and do you see what we need to do in effort to break it up, dy dx? I hope you're seeing this. Take a look. Do you see that I actually have to split it down the middle here? And I'll have to do two separate type 1 regions, one being in that blue color and the other being this kind of mustard color. So I have to set up two double integrals to express it with dy dx. So in that blue region, we're going to fix the x. It behooves us to find this point of intersection here. It's a pretty easy point of intersection. 1, 1 is where they intersect. That's going to be our breaking point. So again, that blue region is going to be fix the x, 0 to 1, and then I have to vary the y. Now I'm just going to use a color here to point to that. So y equals 0 is the bottom, and that is going to continue up to y equals the green curve. This curve here is x equals y cubed, and so y is the cubed root of x. So that's going to help us with our bounds. So at the lower bound, it's y equals 0, and the upper bound is the cubed root of x. And that's f of xy dy dx. And now we have to add that mustard color, and that mustard color is going to fix the x from 1 to the 0 of that line, which is 2. So x equals 1 to x equals 2. And then the y in this case is going to vary from y equals 0 to y equals the line. And so that's going to be y equals 2 minus x. And just to finish it off, f of xy dy dx. Cool. Now to do the integral dx dy, we have to fix the y values. And do you see here that we can do that in one double integral? See, if I shade it going this way, the top, so to speak, is always red and the bottom is always the green, or right left. So that's nice, and that's the desirable property, be able to get this in one swoop, or one double integral. Okay, so we fix the y's. It's going to be from 0 to y equals 1, y equals 0 to y equals 1. And then the inner is going to be, see, we go from lower or left, which is green, x equals y cubed, to the upper or right, and that's going to be 2 minus y. X equals 2 minus y. And then our function, dx dy, this one is a type 2 region. In this problem, we have to choose, or we have to choose to do the double integral dy dx, or we have to do the double integral with dx dy, and the region will dictate our choice. Here I've drawn the parabola and the line, a very poor drawing if I do say so myself, but the drawing nonetheless. So we can find these points of intersection using algebra. We can find that this intersects at 4, 0, and over here intersects at -3, 7 halves. Not all that information has to be important, and we'll see. I want to point out here that there is a right choice versus a wrong choice. I want you to notice that if I attempted to do dx dy, meaning I fix the y, we ultimately have a problem, and this was what we talked about last year in AP Calculus. If you see, if I go this way with a rectangle or summing up little squares that way, the top and the bottom is the same, and I've called that the implosion effect. And because of that, this is not a type 2 region. It is in fact a type 1 region, and since it is a type 1 region, this is the best method that we're going to do. So take a moment and set up this integral accordingly. And we'll see if I beat you to it here. So I'm fixing the x, so I have to see that x is going to go from -3 to 4. Good. And then the y's are going to go from y equals red to y equals green. So from y equals 2 minus 1/2 x to, let's see, solving for y, we have 8 minus 1/2 x squared. There we go. Let's finish this off with f of x, y, and make sure we have the right dy dx. I feel really certain that this is the x coordinate of the intersection and this is the x coordinate of the intersection. And this one, I may have done it wrong, but it doesn't matter because we were fixing the x's. It doesn't matter what the y values were. And one final note on this problem, I guess it is important to see that if you really wanted to do the problem dx dy, you could break this up into 4 regions. We could do this, and we'd have this region here, and then we'd have this region here, and then we'd have to break that up also on this other side, and have 2 other regions. Oh, actually more than 2. Look, we'd need this. Oh boy, this would get really tricky. And then we need all of this. And then finally, we would need, oh goodness, got to pick another color, so many regions. We would need this region here. So if we did in fact want to do it dx dy, we would need 1, 2, 3, 4, 5 double integrals to achieve the same thing we did with the one single integral utilizing the type 1 region. In problem 7, they want us to draw the region. They give us the double integral and they want us to draw the region. Now this f of x y equals this function here. Right now that doesn't matter when we're drawing it. That's only going to matter when we have to evaluate the double integral. So let's draw this region. We have the x-axis, y-axis. So important that we notice that what's fixed, the y is going to be fixed, and the y is going to be fixed from y equals 1 to y equals 3. So along this horizontal band, we are inside this fixed region here. Okay. And then the x is going to be from x equals pi over 6. Okay, let me not worry about that just yet. Let's draw the x equals y squared. So that's going to go 0, 0, 1, 1, and then it's going to come like this, parabola. Let's see if I can draw this without too much. Oh, not too bad. A little pointier than I would have liked, but there's the parabola. And so now that, again, that intersects at 1, 1. So now x has to be from x equals pi over 6. So that's lower than 1, roughly half. And then that's the lower bound of x, and then the upper bound of x is the parabola, so that we have this region that looks like this. That's our region R. Now I'm going to let you evaluate this using the double integral techniques, and in the end your answer should come out to be cosine of 1 minus the cosine of 9 minus 4. So take a minute and make sure that you get that as your answer to the evaluation of the integral. Okay, the last problem of the notes is number 8, and it wants you to set up the integral and then evaluate the integral. This is a rectangular region, and rectangular just means both the x and the y are fixed. Now this is pretty standard notation, so x is going to go from 1 to 4, and y is going to go from negative 1 to 2. So if I set that up, literally x is going to go 1 to 4. The y is going to go negative 1 to 2. Then we have our function 2x plus 6x squared y. And we're going to go dy dx. And I would like you to evaluate this. Grind this one out. It's ugly. It's messy. It's not even worth it almost. But I want you to grind this out to the bitter, bitter, bitter end. And if you grind it out appropriately, it comes out to be